Oxford. so yeah, my talk is actually very nicely complementary to Marcus's wonderful talk, and so basically Marcus in his talk talked a lot about pretty much the state of the art in laser quantum gates, and quantum simulators. So what I want to focus on in my talk is scaling this to a large number of quantum bits. So basically, it's quite obvious that trapped ions have made tremendous progress in realizing many of the components for quantum technology. And so what I'm particularly interested in is the question: how can we really scale this up to large numbers of quantum bits? What's really required to take this instead of 10, 14 to hundreds to thousands, hopefully to millions of quantum bits. Right. So let me start with the people who actually do all the work while I'm having fun in Oxford. So this is my group here, and Björn here sits in the first row. You should grab him later, ask him lots of questions. He's one of my PhD students, and so you can also see in the picture we have palm trees in Brighton, so you can see like it's a sunny country. It's not really part of England. So anyway, so let me start. So let me start first how one would like to trap an ion. You want to have an electric field minimum, but it's illegal in this country and in all countries really. So we can't do that. So we're trying to cheat the system, and we're using a oscillating potential like this. Now we have mostly theorists here in the audience, and so you would now solve the math equations to convince yourself that this actually really can trap something. I'm an experimentalist, so we had an old dodgy record player, so that's how we convince ourselves. So there's a saddle mounted on this old record player, and the motor doesn't really work that well, so you have to help. So now you can see, so the movie plays a bit too fast, but you can see now we put a very heavy ion on top of our spinning oscillating potential. You can see indeed that spinning oscillating potentials actually do trap. And so this is the very principle of any ion trap. Right, so I'm just stopping here because of decoherence, obviously. Right. So let me just give you a very basic summaries of ion traps. This is what we call symmetric ion traps. So show you like a very traditional ion trap. So remember like good old ion traps using metal electrodes, rods, electrodes, and now this is what we call symmetric because the ions kind of surround the ion, and this is what we call asymmetric ion traps because all the electrodes are more or less in one plane and the ions above this plane. The reason why I show you this picture is none of the ion traps we nowadays make look like this anymore, but it shows you the principle, and you can see maybe if you look at this picture that if you look at these type of ion traps, they look more scalable because now all the electrodes are in one plane, and you can now build large-scale architectures, and that's kind of really what I want to tell you about. We're interested in. So again, like this we have Marcus showed the amazing work from Innsbruck, and other groups have also contributed to this, and you can see how far ion traps really are. So the real question is then, why haven't we stolen your credit card details yet? So basically, so what's missing? Why can't we factorize large numbers yet? And so kind of how I see this is exactly with classical computation. We start with a vacuum tube, and I think we've produced them extremely nicely, and now we kind of want to have something like this. I think this probably like this real ion trap quantum computer is going to be bigger than this, so we're certainly not going to have any ion trap iPhones anytime soon. But nevertheless, this is still, I think, the way to go. So the idea is kind of it's a very kind of basic idea of having somewhere where we can store quantum information, somewhere where we carry out entanglement operations, and some way where we can transport quantum information. The way I'm drawing it here is via shuttling. Now this already is a very naive picture, I would say, because in order to make architectures you need a lot more than a few trapping zones. So architectures really incorporate a lot of things like generation of analog voltages. So if you want a million ions in here or a million trapping zones, you're going to need quite a few million voltages, you may want to have cavities or mirrors basically incorporated. You may want to have a lot of other more advanced features, which then make this an architecture rather than just a trapping array. So basically, the whole baseline of this talk is basically this. Ion trapping, you know, everybody knows that atomic physics is nice and wonderful and clean. And so what we've done then is we went to condensed matter and stole all the good stuff. So basically, condensed matter qubits are kind of pretty horrible. So what we did is we took the scalability and transferred it over to the nice qubits. So the idea is really to build something which is inherently scalable and mix it with something which is a wonderful qubit. And so kind of this is kind of how we intend to build these large scale architectures. So just to show you like the way how we operate these things, this is a vacuum system, and you have so you have a chip carrier basically. On this is your chip is mounted, and you just plug this basically into such a receptacle mount, which is inside your vacuum system, and you bring your laser beams in from all different sides and so on, and that's the way how you can mount these chips. This is a typical vacuum system in our lab. You can see here the side windows, the chips that's here at the front. So there's one thing which is which many years ago people a bit worried about how small you can make these ion traps is anomalous heating basically, and so for us making these traps very small, we want to measure this. This is a way you can measure this basically very simply. You basically turn on your cooling laser for a variable delay time, and as you turn on your laser, you monitor the fluorescence of the ion, and as you monitor the fluorescence of the ion, you can then deduce the motional state of the ion. And we've done that, measured this for terbium, which is this point here, which is fine. And so that was something we were worried about. Maybe terbium coating has an impact. In fact, nowadays we know exactly how to minimize a anomalous heating via things like argon, shooting in argon ions on the surface of things like helium ions at the surface, and we can now build reasonably small ion traps, and so this is not so much of an issue anymore. Now, we do work towards entanglement gates, and well, the Innsbruck group has done extremely nice work in doing this using lasers. What we're interested in is using a different method. We try to use microwaves, and microwaves are very nice in the sense that they're much cheaper, and they may be much easier to scale up if you want to really go to large numbers. So this is, let me just quickly show you, this is our ion. We use a terbium. We like a terbium, but there's no real perfect ion, but terbium has a lot of advantages. For example, the large, fine and hyperfine structure, which has some advantages. So basically, this is the way you detect terbium ions, so that you get a histogram, basically, and so you can see here, like we have a resonant transition here, so this is our one qubit state, and you can see you detect a lot of fluorescence, but now if the ion is in the other state, these beams are off resonant, and basically you get a different histogram, and by differentiating between these two histograms, you can deduce the quantum state. This is just Rabi flopping, and quite bad Rabi flopping, but we're only just getting started, and my students are just working on to make this one contrast, which is actually rather simple, so I shouldn't have really shown this picture, but it's just on in the works basically. So again, like I started talking about entangling gates. So basically, you need some kind of state-dependent force, and that's usually done using some kind of Raman transition. But now, if you want to scale this up, you're going to have to imagine you don't want to run these gates one after the other. You want to run them in parallel. So if you think about it, if you have lots and lots of these trapped ions everywhere, it's going to be very costly. So there's better ways, I feel, to do this, or possibly not better ways, hopefully better ways, and certainly much cheaper ways. This is using microwave radiation. And so with microwaves, kind of, there's two schemes out there. There's one where you use static magnetic field gradients with an external microwave source, and another scheme where you can use oscillating magnetic field gradients on the chip. And I'm going to show in a second, but I believe this is the way to go, certainly for us. But let me first explain quickly how this thing works. It's basically like, with microwaves you can't really drive motional transition. And that's kind of the problem, because if you want to do quantum gates with trapped ions, you need to drive motional transitions. But the Untitled parameter, or basically the wavelength, the K vector of the radiation is just too small, so you can't really give an ion a kick. So basically now, there's a way to trick the system how you can do that nevertheless. And the way you do that is you prepare the ion in a state where it gets a kick. If it basically you prepare it in a state where in one state it is not sensitive to the magnetic field gradient, in the other state it will feel a force if there's a magnetic field gradient. And as you rotate the ion now into this state, if there's a strong magnetic field gradient, it gets a kick. And so basically this way you can trick basically the ion of getting a trick, even for the rotation itself really couldn't give that kick. And so that way you basically can get like an Untitled parameter basically, which is now a function of the magnetic field gradient. And so this kind of tells you something about the speed of the quantum gate, and you can see that it is now a function of the magnetic field gradient you can produce on your microchip. So this is a entanglement microchip, and in fact Bjorn has designed this thing, so ask him lots of questions after this talk. And you can see here basically they have basically trapping electrodes in a surface, but you have this extremely thick wire basically which allows us to carry very, very large currents. And just to give you an idea, the first gate with this method was actually just done a few months ago, and there was 10 Tesla per meter available on that particular experiment, and we were able to produce around 100 Tesla per meter. So you can see that doing this will hopefully drive up the entanglement fidelity quite significantly. So in terms of making geometries, architectures, you have to ask yourself, what are optimal geometries for these ion chips? And I'm just going to give you a few considerations we've gone through. I'll go fairly quickly first. Please ask questions if you want to know details. So first of all, these surface ion traps are not very, very deep. So by applying a certain voltage, the potential isn't very deep. So we had a bit of a look, how can we make them optimally deep by optimizing these dimensions. And here this is a graph basically shows you like how wide you have to make these electrodes to make them optimally deep. Now next step is basically, if you want to run a quantum algorithm, basically you have to bring ions together, you have to separate them again. And as we all know in life, separation can rather be difficult, and for trapped ions that is indeed the case. So basically the way you do this with trapped ions, you have some kind of potential like this, basically a quartic potential, and using this quartic term you can then produce a double well. And now this double well, basically, in order to produce this, you're going to have to go, you start from just a potential like this, and then you basically come to a flat potential like this, and then you produce this double well. Turns out, the weakest secular frequency, the weakest frequency in this transition to produce this double well, and remember that's you need to separate two ions, the weakest secular frequency depends on this beta here, so the quartic term of this potential. And so basically now, in quantum computing you want to do things very fast. You want to do them adiabatic, but very fast. And so this frequency that basically is your speed limit. You can't transport faster, or you can't separate faster than this frequency. And this frequency depends on this beta factor. And so we had a look how we can make architectures to maximize this beta factor. And again, I won't show you the details, but these graphs show you basically how you have to pick the dimensions of these control electrodes here to make this beta parameter maximal. And I'll just jump over this graph. This is just another, basically tells you again the width and what width you want to use here. But what I want to talk about is basically here the evolution of the secular frequency is during the separation process. So basically, as you produce this double well, you get this very small secular frequency right here. And what we've done is we solved the equations of motion to kind of see basically what that actually means for separation. And so what you see here, basically, this is the motional state of an ion as a function of how long it takes for you to carry out the separation. And this is basically, this curve is the motional state excitation. So basically you can see that basically if you take longer for the separation process, obviously excite less motion of the ion. And I'm showing here two cases. One is for center electrode segmented, and one where the center electrodes aren't segmented. So these are two types of ion trap architectures. And you can see here basically that obviously the longer you take, the less motional excitation you get. But the problem is here that this anomalous heating effect, what I showed you before, produces also motional excitation. So basically geometries like this have a hard time to adiabatically separate two ions, because where these lines cross, so this is the curve for heating, that's the curve for anomalous heating and for the heating due to the transport process, where they cross basically that's the best you can achieve. And so this is kind of, using that you can see that architectures which have a center segmentation are much more suitable. Now don't look too closely on this number. This number is really only for illustrative purposes, because it really depends on the particular anomalous heating rate of that particular ion trap. And so this is very conservatively chosen, so geometries like this can perform much better than I'm showing here. But I'm really only showing this to compare this to this, and you can see center segmented architectures work better. What about junctions? So if you want to make these architectures, you need junctions. And this is an experiment we did many years ago, in 2005. And that was the first two-dimensional ion trap junction actually. We shuttled an ion around the junction here to this point. The problem, it was a very difficult experiment. One of the reasons why it was difficult is because there were potential barriers in the way, and when you shuttled around the corner, the ion gained a lot of kinetic energy. And so in order to adiabatically shuttle, you don't want to do that. And so basically, one thing we are now interested in is how can you make junction and surface ion traps which do not have these potential barriers. So the way to do this is you can calculate the field, and we use in fact a Biot-Savart-like line integral method to calculate this, and what you get is optimized geometry. So this is a non-optimized junction geometry. So you see the electrodes here, these are the RF electrodes, and if the electrodes look like the ones here drawn in red right now, your barrier is quite significant. So the ion, as it makes it through that junction, has to cross a significant energy barrier. Now a very simple trick, using this method we can amend our junction slightly, and you can see now this is the amended junction. Now you can see the barrier is very small. This is the potential now with this optimized junction. In fact, this is another junction. This is a junction beyond design actually. You can see here this is a non-optimized junction. You see a massive energy barrier as the ion crosses that junction. If you now make an amended junction, you can see now here basically the ion hardly sees an energy barrier anymore, and again can now shuttle adiabatically through your junction. Right, so this was just a few things I wanted to say about geometries. There's a lot more considerations, but just want to give you a flavor of the things we're interested in. So the second thing obviously is to build ion chips, and if you're interested there's a lot of different processes and methods how to build these ion chips. We've put an overview paper together, so if you're interested, this is a nice place to look. But let me tell you how we now actually fabricate these devices, these microchips, and we use around 4 different process designs to do that. And so I'm going to talk about 2 of them right now, just to give you again a flavor of the stuff we do. So the big challenges in making these ion trap architectures or arrays is you don't want to have any exposed dielectrics, because dielectrics, as they charge up, produce uncontrollable electric fields, and that makes making quantum gates very difficult. You want to increase the voltage you can apply as much as possible, so you can make deep traps where you can store your ions forever. If you want to have 1,000 ions, you want to entangle all of them, it may take you some time, and you don't want to have to lose your ions in the process constantly. You want to get rid of these large ion heating rates. We have now ways to do that, for example by bombard the ion trap and basically clean very thin layers of carbon of the surface, Geometries, I talked about that. You want to have optimized geometries, and most importantly, the ability to really scale this up to be able to say, yes, we can have hundreds, thousands, millions of ions eventually in a geometry. So, but let me start with some material science first. Like, I'm an atomic physicist, and in my last few years, I've had to start appreciate dirty material science and condensed matter physics. So this is, for example, a very basic thing which is highly relevant, and this is how high voltages you can apply to these arrays. They're very small, you know, there's micron separations, but you want to apply really, really large voltages. So we were interested in how does material science come into this whole thing. So we put together some very simple experiments, just basically electrodes with a variable separation. We measure basically the breakdown over this dielectric, and this is the theory behind it. So it's secondary electron emission avalanche, which leads to basically a surface flashover. And won't have much time to tell you more about these fudge parameters, which from my atomic physics kind of view I would probably call them, but there actually are some numbers out there, and you can actually start to understand these things. So that's kind of what we went through and try to really figure these things out. And so first we started with different samples. First we started on quartz, and later on I'll tell you in a second why we went then on a PECVD deposited electrodes. This is basically just the experiments. You can see for breakdown this looks nice. After breakdown it looks like somebody's eaten a little bit out of the electrode. For the case of RF, for DC breakdown you get a very catastrophic breakdown. These are some of our first results, and you can see that we can nicely tell basically how much voltage we can apply for what electrode separations that allows us to basically plan optimal ion trap geometries. However, it would be nice if you can double this. What about if we can just apply twice as much volts over a certain separation? This has a lot of applications, not just in ion traps. In any kind of MEMS fabrication devices, you may want to apply really large voltages, and this is the limit here. So what are you going to do? So we did a bit of playing around with stuff, and here's the first result. This is quite fresh. Now, by using a slightly different dielectric surface, we could double the voltages we can apply over a certain gap size. And so this is a very, very huge impact on basically how we can make these ion traps now, because now suddenly you can see we are able to have very, very small electrode spacing, nevertheless apply quite significant voltages. Right, so let me start with actual trap chips. This is first, let me start with no center segmentation asymmetric ion traps. So there's a good reason why you want to also build them. Now I'll tell you in a second, but let me first start with the fabrication process. Since we don't have many fabricators here, I'm going to zoom right through the process basically, so you can kind of see the process here. We start with silicon-on-insulator substrate basically. We do various etches basically, and we end up with a structure like this. This is the structure basically, and now this is the actual chip, the finished chip. And again, we kind of went out of our way to kind of be able to apply large voltages. So you can see this is the side view of the structure with a typical edge used for these structures. So this is actually the junction here. As you can see, these are the electrodes basically. The ions are being can be moved basically over this junction. But again, I want to show you some material science because that's again quite relevant. You can see here basically this is kind of like a typical edge, and you can see here the breakdown would occur as a surface flashover between this point and this point that will lead to a certain breakdown voltage. What we've been able to do is we cheat the system, and now we have a different edge which kind of leads to a surface like this. And so suddenly our area where the surface flashover will occur is now very, very large. And what that means is that we can apply significantly larger voltages. And just to give you an idea, basically, this is the breakdown voltage over the structure. And just to give you a feeling how this has changed, we built actually the very first monolithic ion trap chip in 2005 when I was working in Michigan, and we could apply voltages of around 5 or 10 or 15 volts. Now this device we can apply 1200 volts, so you can see it's nice. For experimentalists, 2 orders of magnitude is certainly something we do like, so that allows very, very deep ion traps and steep secular frequencies. Next device I want to talk about is one which allows for center segmentation. So basically you have again electrodes like this, but now suddenly you have under Earth basically delivery lines basically where we can connectorize electrodes which are not connected otherwise. This is the picture of again the device. You can see these undercover lines in the junction here. This is the fabrication design. Let's click right through this. This is the fabrication sequence. Again, I won't bore you with all the steps basically. You start basically with just a normal substrate, and we have various layers of. This is a metallized ion trap. So this is basically all gold, and you can see here. So this is very very high aspect ratio electrode basically. So the dielectric is not exposed at all to the ion, which now will sit up there. You can see now you have basically a connection under the substrate. This is the actually this is mainly a beautiful picture, but I'm showing this anyway. Doing this stuff is like it's gotta be you love the pictures. So this is actually what you see here is photoresist. But the one slight justification why I can show you this is it shows you the high aspect ratio, what we can achieve with this photoresist. That took us quite some time to make this work properly, especially the electroplating part. But let me, beyond the beautiful pictures, I'll show you actually the finished device, nearly finished device. This is now the actual chip basically. You can see the center segmentations, you can see the undercover connections, basic under earth connections, which now lead to the outside, and I think we just removed or about to remove the final adhesion layer at the bottom, which allows us to use that device. Right, so again, that's a center connect. So basically, the question, what I've shown you so far is architectures which kind of operate with shuttling, but there's other options like cavities, superconducting wires, and stationary lattices. And the latter we're actually quite interested in, so we're interested very much in building quantum simulators. So this is basically our approach to do that. So we build two-dimensional ion trap lattices. And so basically use again this first method I've showed you using SOI, silicon-on-insulator substrates, and so we basically have a lattice like this, a laser beam which can now, in fact a sheet of light which can now address all the ions above the surface. This is the mask, so you see like your array of ion traps in a two-dimensional lattice. Again, using this little etching trick we can achieve quite significant trapping depth, so we can actually keep our ions and they don't get lost. This is the actual chip, so you can see here the electrodes, the two-dimensional array, and we are just about to start operating this device. So, so that's right in here. So I want to, we have done a little bit of theory as well on two-dimensional quantum simulators basically, and I'll tell you a bit about this. So basically, if you want to do quantum simulations using this device, using these devices, what you're interested in is really the coupling rate. So that's the coupling rate that depends on the state-dependent force, and it also depends on this geometric parameter here. And that really depends on the particular lattice. A geometric parameter is basically the ratio of the interaction between two ions in separate sides over the force the ion feels in each individual side. So basically that tells you something basically about how one ion interacts with another ion in another well. And you have to get this beta factor significantly large in order for ions basically in order for you to be able to entangle ions in separate wells. So for this device I've shown you our beta factor is 10 to the minus 6, which is okay, but it would be nice to have this larger. So basically we've started to trying to understand how we can make architectures optimal. So how would they be optimal? And the two time scales to consider are the decoherence time, and the decoherence time in this case is mainly given by the anomalous heating rate. So basically if an ion is close to surface it will feel emotional excitation, and if you entangle via the emotional state, then during the entanglement, only during the entanglement, not after the entanglement, but during the entanglement, decoherence is given by anomalous heating. So and obviously you want to have your interaction time faster than your decoherence time. So that's kind of, so basically what we look at is this K-sim, which we define as the the coherence time over the entanglement time. And so we're trying to optimize this, so we look at general lattices, and so these are typical lattice structures basically. And if you're interested in this, we've put a paper on the server about this. So basically, first of all, we want to make the interactions in the array all equal. So this tells you basically what you need to do. You need to vary this distance here, the distance from the outer electrode to the end of the array. And if you vary this, you can produce interactions. This is K-sim basically for each lattice side, and you can assure that K-sim basically is homogeneous over the array. And so this tells you that in order to make homogeneous lattices, you're going to have to vary this g over the width of the lattice, but it's a number of the lattice sides basically. So this basically is a recipe how you make any kind of lattice you want to make homogeneous. This is that answers the question how many polygon sides your electrode needs to have, and in fact it turns out circular is probably the best, but you want a polygon of at least around 20 sides, then basically you get to optimal K-sim. So round electrodes are good basically, you take a message from here. So then what we've done is basically we calculated K-sim as a function of polygon separation and polygon radius, and found basically what is optimal, basically what polygon separation and radius produce optimal geometries, and these basically are the results. It's a function of the number of ions or quantum simulator sites, and the problem is actually scaled with this parameter here. So this gives dimensions in micrometers, but it's actually scaled with this scaling factor, which is the voltage over the driving frequency of the ion trap. So basically, you need to think about what alpha you can afford in the ion trap array, and then we can tell you what radius and dimension these lattices need to be. This is all a bit more complicated, but really don't have time to give you all the details here. But basically, what this shows you is basically a example situation from our calculations where you can show that we can build, and we've got one of these devices in fabrication where you can build the quantum simulator using a K-sim of 2 and an error of 0.1. So quite a reasonable basically quantum simulator using these dimensions, and this tells you basically the laser power and the tuning, things like that you need to use for this device. This is an example for your turbines. So another project we just started, so I won't talk much about it, but we'll just give you a little idea, is addressing quantum hybrid systems. So you've got this really crazy idea of coupling superconducting qubits and trapped ion qubits, so this is a collaboration with some other European partners, so we literally only just started this, and there's a lot of technical challenges if you want to achieve that. And in fact, so let me just give you a few of the things we're going to do as part of this project. So obviously, again, it's developing the optimal ion trap geometries, so we can transport the ion from a vertical high distance very, very close to a superconducting cavity. So basically the idea is to have a superconducting qubit, couple that to a superconducting cavity, and then you couple the ion by a superconducting cavity. When in fact, an ensemble of ions, that will be very, very difficult. So this is an extremely challenging, very, very long-term project, and we only, even within the 3 years, we only really aim for classical coupling, but tackle some of these rather difficult problems like making flat multiple ion traps, so you can have more than one ion, possibly going towards Rydberg ions actually. So we're going to hope you learn lots from you about that. So then you need to really operate these things at a cryogenic temperature, and not only just at 4 Kelvin, but eventually in order to access the high Qs for the superconducting resonators, we need to do work in actual dilution fridges. So this is going to be quite a challenge to trap ions in a dilution fridge. But again, we love fun challenges. So so basically, initially what we're going to work for is coupling resonators, basically microwave resonators with trapped ions, and there's obviously a lot of applications doing that. Also, just in, for example, in operating microwave iron gates. So this is going to be really exciting stuff. We're quite excited about that. So finally, in the last 2 minutes, I'm going to quickly tell you about something we just started as well. Is our first rather dodgy attempts to look at the Kibble-Zerg mechanism in ion traps. So basically, turns out the number of defects created when you do during a continuous phase transitions is predicted by the inhomogeneous, in this case, Kibble-Zerg mechanism. And there's a lot of things in nature which are governed by this mechanism, and you can actually simulate that using ion traps. And so this is kind of a little picture. You can see, like, as you start with an ion trap string, and then as you quench it, you get a zigzag configuration. And so this is what we're kind of trying to do, is basically you vary the quench rate, and it turns out if you vary the quench rate, then you're going to get these defects. So this is a paper which first predicted the occurrence, the scaling of these defects. Basically, so you get defects in these zigzag transitions, and so this is something we're interested to reproduce. So this is a simulation. One of our collaborators in Ulm. And it basically, this works. So basically, you can see, like, basically as you quench, this is exactly for the parameters in our experiment. More or less, you can see the emergence of a defect right in the center. There are some other defects, but they move out. So it's a bit complicated to see in the experiment. I found it's actually quite difficult to see this. And so basically, this is a picture, and you can see that this is. We have even some impurities in here, but this was just our kind of playful attempt to see this, basically. So we quench this basically through, but we have a lot of problems basically with this. Basically we have an oven which can't really isotope selectively load, and to access the parameter regime, which is required to see these defects, we needed a different ion trap. So we see a lot of micromotion basically if we access the parameter regime, and so basically we've designed an ion trap, come back to our microchips basically, which is exactly capable of accessing this parameter regime. So hopefully very soon I'll be able to show you some results on this. So with this, I think I've covered everything I wanted to say. So thank you very much for your time, and if you have any questions, please.
Other questions concerning how to scale up?
You had this junction, these lattices of holes. Is the idea that you have one ion in each hole, or is this the...
That's right.
And then they're coupled vibrationally from one hole to the next?
Exactly right. This vibration coupling is rather difficult. Basically, usually they're far separated, but far away, and they really don't feel each other. So basically, it's very challenging to make each ion feel each other, even though they're trapped in a separate well. And this is the difficulty in optimizing these geometries.
Another very naive question is, because you were talking about these, if I understood, a lot of these traps, you're designing them and making them for the moment. Just from outside, what is the probability that a trap, this thing that you've made, actually traps ions, and know that it doesn't work?
Yeah, I think this, like, we're very fortunate. There used to be a time, I remember when I did build first ion traps, like I was working in Michigan, I would have said the probability then was rather low. So nowadays, I think we've learned a lot about making ion traps and making fabrication processes which work. So I really haven't had time to talk about a lot of the subtleties about the electric equivalent circuits and things like that. So we've learned a lot, basically. So I'd say if a device, if the fabrication goes right, the probability is probably 95%. So it's quite high. There's no surprises anymore. We understand these things, but obviously sometimes the fabrication processes I showed you are super highly simplified, and so it's basically like learning to cook, and each process step basically takes a lot of development. Often they're very atypical process steps, because typically people etch through hundreds of nanometers. We etch through 10 micrometers. And so that's basically what takes so long to develop these devices, is to actually develop the processes.
What lithography do you use usually?
Sorry?
What lithography do you use in your process?
It's all photolithography. It's basically, we don't need E-beam because basically the dimensions, as you've seen in the breakdown measurements, are kind of, we don't want to go much smaller than around 5 microns. So it's actually just on the edge of photolithography. In fact, Björn just told me the other day that for one particular trap, he would be tempted to go E-beam because, you know, with one micron or things like that, things start to become a bit edgy. But it's super, for everything we've done is photolithography.
So if you note one of these atoms in a certain position and then transport it, is the T2 with distance known, or how does that compare to just leaving out at a point?
Yeah, there have been done experiments basically. I mean, the T2, basically, fundamentally, I want to really stress this, like, because before I talked about decoherence and I used anomalous heating. Usually, anomalous heating is no decoherence, because usually the quantum information is stored in the internal state of the ion. So only basically during the actual time when the quantum gate occurs, or when the Hamiltonian evolves, basically, then you're subject to this. So basically, there have been some experiments done measuring T2 time, and it's still seconds. So it's not really much of an issue, basically. It becomes an issue during the actual gate operation, which can take anything between maybe 5 microseconds to 50 microseconds, or something like that. And heating rates are luckily very small during that kind of interval.
Any questions? Maybe I have one more question concerning the, you mentioned some special treatment with argon to reduce the heating rate.
Yeah.
What special is this happening there?
It's a beautiful result by the NIST group actually. Literally, just went on the server and we got our own argon ion beam in our vacuum system. So basically, what they found is that if you clean the electrodes, basically, there seems to be a thin monoatomic layer of carbon on the electrodes, and basically you can clean this off. And they managed to reduce the anomalous heating rate by 2 or 3 orders of magnitude. And that same reduction you can achieve with obviously with using cryogenic vacuum systems. But obviously, if you can just do it that way, it's much
I think
easier.
there's an additional possibility then to cool that and to even further reduce the heating rate, or?
That's a very good question. In fact, that's exactly what we're going to do. So I will let you know. but I don't know. I really don't know the answer to this question. But I wish I would. But I don't think anybody really understands it yet. I mean, these guys. We're quite clear about this, that they really don't quite understand yet the process. So I think we need to do a lot more work to fully do this, and I think just trying is probably the best way to find out.
No further questions? Okay, then I think we should continue.